Good morning. Hello, good morning, everyone.
Good morning, sir.
I can see 10 people have joined so far. Hope you all can hear me. Can you hear me?
Yes, sir.
Okay, sure. So today I might have to stop in the middle because I'm not in the usual place. So there are some difficulties here. But anyway, I will continue until as much as as much as possible. So last time we discussed about the Earth's processes, right? The all the processes that we encounter as tectonic processes, right? Remember, collision, uh, ocean-ocean collision, continent-ocean collision, and continent-continent collision. So the typical examples for this is, for example, the Japanese islands. That is where you have the ocean-ocean collision, plate collision. That's why uh, this type of chains, island chains are formed, which is uh, equal to the formation of Japanese islands. We call them island arcs. Okay, because of this subduction, these type of islands are formed, right? So that is ocean-ocean collision, and also the same similar situation is the Mariana Trench, where deep trenches are formed in addition to these island arcs. And continent-ocean collision, where you can see huge mountain belts are formed on the continent side because of this volcanism. For example, is Andes Mountains. And the other one is the collision between continents and continents, where you can see huge mountains, belts are formed. A series of mountain belts are formed, similar to the Himalayas or European Alps, even, right? So all these the belts are being uplifted. That means their elevation is getting higher and higher, little by little, as this collision progresses. But once it comes to a maximum collision point, uh, the maximum compression status are achieved by the two plates, and there will be no more uh, uplifting. Instead, there will be some rupturing in between the plates somewhere here, so that you may have uh, like earthquakes and all, right? Even in the continent. So accordingly, these movements are happening in different ways. We can expect geodynamically unstable uh, crustal fragments in our Earth. The reason is this plate motion. The initial force for this plate motion is uh, simply the mantle convection, because that drives the plates, and because of that, all these various types of collisions and subductions are taking place. That's the reason for all these collisions and subductions. And if we consider, so far we considered about the convergent plate boundaries, that means the movements towards each other, convergence. Now let's move to the divergence, that means divergent plate boundaries, which means the two plates are moving away from each other. So I think you can remember where we were looking at a map where you had the tectonic plates, and these tectonic plates can also move away from each other. For example, here, North American plate is here and the Eurasian plate is there, right? So I think you can remember the plate map right? So for example here, you have the North American plate here, right? This one, and Eurasian plate there, right? So these two plates are moving away from each other. See these two arrows, and the boundary goes in between the Atlantic Ocean, and you have the Iceland there. You have the Iceland there, and this boundary goes straight away in the middle of the country. Okay, so it's very dangerous place because the country is being pulled apart, right? So soon it will be fragmented into two countries. So that happens naturally. So that is the situation there. For example, this is the situation. So you can see in the middle of the country there are volcanoes, huge volcanic belts. So this upper image shows this splitting region, right? This one is the image shown by here. So you can see lava flow, magma flows, lava flows are there. So this is a plate boundary, divergent plate boundary, because plates are moving away from each other. There will be some vacuum like place generated, and this to this vacuum what is happening is magma is coming up, flowing out, right? So it's entirely volcanism is taking place. So this is what we simply call the continental rifting. Continental rifting means this phenomena. Okay, two continents are rifted, that means fractured, and magma is flowing. So this is happening at divergent plate boundaries. So we have all these convergence and divergence together in the setting of the Earth's crust. So convergence is always subduction and then final collision, right? Subduction, and it ends with the collision, or otherwise just a collision between two continental plates. Uh, the divergence is the mid-ocean ridge. So submarine volcanism happens if it directly relate with an oceanic plate. When it continues with the continental plates, for example, this is the continent, there will be surface volcanoes as well, right? So this is divergence and this is convergence. So these are the places where volcanoes are generated in the world normally. Okay, and even in the continent itself, I said within the continent there can be rifting zones, not like exactly with related to this Iceland situation where you have the clear two plates are moving, but in a single plate also, for example here, within a single plate also there can be some divergence that is possible, right? So all these situations refer to volcanoes where this friction or just heating and magma flowing causes volcanism to happen. It might be submarine volcanism or subaerial volcanism, that means on the surface volcanism. Okay, so subduction, rifting, and hotspots. Hotspots, you can remember, I think, hotspots, we specifically refer to the places where the huge magma flows are coming from very deep part of the mantle, I mean, crust mantle boundary. The normal magma is coming at a depth somewhere here, right? Asthenospheric depth. It's not very deep. It's like 50, 60, even maybe that shallow kilometers, okay? Or maybe 100, 200 kilometers deep. But hotspots means some thousands of kilometer deep. That means core mantle boundary that is very deep down there, and that magma is coming up like the places where we talked about hotspot volcanoes in regions like Hawaiian Islands. Hawaiian Islands are products of these hotspot type volcanoes, right? So this hotspot magma is different from uh, these mid-ocean ridge basalts or mid-ocean ridge magmas or rifting magmas, normal continental rifting magmas, because not only by their physical properties like temperature and pressure, but also their chemistry is also different, right? The chemistry is also different because in the deep in the mantle, the chemistry is different than what is available in the shallow mantle levels, right? So These type of differences are there in magmatism. You can expect, right? So please everyone put your name and number in the chat box, okay, to mark the attendance. So these type of volcanoes are produced, and hotspot volcanoes, if we consider, as I mentioned, it is coming from very deep part as a mantle plume. We call it a mantle plume, and that comes to the shallow levels and then uh, flows as a mantle plume. Right? So the Hawaiian island chains are examples of these volcanoes, hotspot volcanoes. We call them hotspot volcanoes. These are volcano from Hawaiian Islands. So these are very, very explosive type, uh, and it's very dangerous. These types of volcanoes, right? So every day there are flowing magma flowing when this type of mantle flow is there, right? So this connection is continuous for millions of years, right? This mantle flow plume connection, once plume hits, everything is splitted. The continental fragments are uh, broken into pieces, but the magma flow continues. Right. That's why still Hawaiian Islands have these active volcanoes. Yeah. Okay. So this continental configuration is driven by or controlled by mantle plumes as well, right? So as I mentioned, every 300 to 400 million years time, there will be a mantle plume. So that reshapes the Earth, right? So the current configuration of continents, what we have in our mind as the world map will be changed every 300 to 400 million years time, right? This happens as the supercontinent cycle. So the supercontinental cycle is controlled by mantle plumes. So this is we are expecting uh, another mantle plume in another 150 or 200 million years later. Okay, that is the time for the next mantle plume. So the world map will be changed after 100 million years time, right? None of us will be there. Okay, so as I mentioned, the tectonic plates, the biggest tectonic plate is the Pacific plate, where you can see all the margin of this Pacific plate. This is the Pacific plate. All the margin is marked with volcanoes. These are the these are the volcanic points. That means not necessarily the hotspots, right? It's just the normal mid-ocean ridge volcanoes, because rifting and all subduction, divergence, everything is can be happening, right? So volcanoes are all located around the plate, and that is what you refer as Pacific Ring of Fire, because it's a volcanic ring, right? You can see almost everywhere there are some volcanoes, right? It's a ring like. Right? So this is the hotspot volcano in the middle of the plate. Right? That was happened some time ago, but still continuing. Some active volcanism is still continuing. At the same time, this type of mid-ocean ridge type volcanism is also continuing. This is shallow volcanism, like what you expect in these regions, right? These ones, but the hotspot one is the one coming from very deep part. Right? Previously, this mantle plume was hit in the Pacific region, and all these continents were broken. That's how this Pacific Ocean was also formed. Previously, this part was entirely of continent, right, full of continents. But after hitting the mantle plume, one part moved there and the other part moved there, opening the Pacific Ocean. Right, that is what has happened in the recent past. Right. So these are the volcanism types, and if you consider the active volcanoes in the world, you can see most of these volcanoes are related with plate margins, right? These yellow spots refer the volcanic places, and also you can relate them with the tectonic plate margins as well, right? So all these things can be, I mean, the locations can be related with some sort of a tectonic situation, right? So that's why you can see these volcanoes located along the plate margin. So along the plate margin, not only volcanoes, major earthquakes are also located. So even if you plot the earthquakes occurred around the world, it will also follow these continental marginal places, right? Sorry, continental and oceanic marginal places. That means plate boundaries. Luckily, we are away from a plate boundary. So, for example, here you can see we are in an Indian plate, Indo-Australian plate together, but away from a margin, right? So, we are in the middle part of the plate. So, therefore, we have no risk of volcanoes or earthquakes so far, but some tremors has happened as a result of some nearby plate boundaries. For example, here there can be some new plate boundaries generation because of this rupturing. It can happen at anywhere if the compression and extension continue. So such influences are there, but not direct volcanoes. So we are not in an active volcanic active earthquake terrain. Okay, so that is the situation with respect to the tectonic forces. So and in the today I haven't prepared the video clip. So next time in the next lecture I will present you some video clips related with these processes and these phenomena, so that you will have some better understanding, clear understanding about these processes. Okay, so do you have any questions up to this section, up to these points related with Earth's processes and structure? We still have some little more to discuss. If you have any question, you can ask. Or otherwise, we'll move to the uh, next part, where we have to discuss the same thing, but in a different way. Uh, for example, you can see here some lecture, some very special lecture note I have referred here, where we relate this all structure with the Earth's uh, P and S waves, P waves and S waves. Okay, P waves and S waves. That means compressional and shear waves. Those are seismic waves. So, in other words, we call them earthquake waves as well. Right? Actually, these waves are very useful to understand the Earth's structure, because by penetrating these waves, the changing velocities uh, are used to uh, figure out the structure, right? So there are two types of waves. I will present you some figures later on. Uh, these are called P waves. P waves are referred as compressional waves, and S waves, which are referred as shear waves. So P waves means compressional means like, for example, if you are taking a uh, slinky. So you understand slinky. It's a coil, right? Coil like thing, spring, for example, spring shock absorber like thing, right? The spring can absorb the pressure, right? So once you release it, it releases energy. How it releases energy is in terms of a wave, right? So that is what you call compressional waves. So you can compress and dilate, so like that. So those type of waves are called P waves, and S waves are the shear waves. Shear wave means their motion is different, their properties are also different. That is like, if you try to like shearing, you understand, I think, the shearing, the faulting, right? Two rock layers moving away from each other parallelly, but in different but in opposite directions. For example, if you want to tear off a piece of paper, you have to apply two forces onto the paper. You take a half sheet and you try to tear it off, right? You apply two forces in two different directions, but parallelly, isn't it? Otherwise you can't tear it easily. So that sort of waves are called shear waves. So these two types of waves are available related with earthquakes, actually naturally or happening when earthquakes are generated. But we can artificially make them and make them penetrated into the Earth's interior, so that you can observe the Earth's interior with the change of velocities. Okay, with change of velocities, you can expect uh, the change of velocities. So, for example, this velocity depends on the density and the elasticity properties of the Earth's material, the penetrating material. Okay, so density and elasticity is very important. So generally, speed increases with depth due to pressure forming a more compact elastic material. So when you go deeper and deeper into the earth, the pressure increases, right? So this pressure increases, and it's more compacted, like. So therefore, the velocity is supposed to be increased for these seismic waves. So uh, another property of P waves is they are able to propagate through the liquids as well as solids. Not only solids, but also it can go through the liquids. But S waves cannot travel through liquids. So that means if you penetrate these waves into the Earth's interior, uh, it should not penetrate into outer core, right? Remember, because outer core is liquid. So there should be some change in S wave velocity or complete disappearance of S waves. So these type of properties of these S and P waves are used to understand the structure of the Earth. So actually, the crust, mantle, and core has been understood. I mean, to be existing, physically existing. The idea has come through the P and S waves, right? So these waves travel at different speeds. Normally, P waves are faster than S waves, right? And also it changes depending on the rock type and mineral type. Okay, rock type and mineral type, they are changing. So actually, I'm experiencing a difficulty in the power. Okay, so because I don't have the power connector, this is a Mac computer. It's not compatible with any other power adapter. So I'm in a different place now. So therefore, it's a little bit difficult for me to continue. Maybe a little more I can continue. But if I discontinue, please uh, excuse me, because today I'm entirely lost with this technical thing. Okay, I haven't got the power adapter right now. Okay, anyway, so we will continue. We can present the seismic waves traveling as wave fronts. So wave front means like the beams, like for example, light beam, right? So that light beam travels through the Earth's interior, so that it penetrates in the materials at different velocities. So in the seismic waves, people have understood some abrupt changes means sudden changes, so that they think that uh, at particular depths these abrupt changes have happened due to changes of material. Changes of material means changes of rock types, actually. Changes of rock types, right? So these changes are referred as discontinuities, right? Or these discontinuities later on figured out as the boundaries of layers. Okay, so actually the density is also different with respect to the rock type. As you know, the crust is composed of mostly aluminum rich silicates, and mantle is composed of mostly iron and magnesium rich silicates. So therefore, uh, these layers are entirely different, right? So they propagate. The P and S waves propagate differently there, so that it helps us to locate these depths, these boundaries, right? Because when these seismic waves, they have the ability to reflect and refract as well. Refraction, refraction means bending of waves, right? When you send a wave from one medium to another, for example from air to water, if you make a torchlight to the water, that light wave bends. That is what you call the refraction, right? Bending. Reflection, already. It's like something like acting like a mirror, right? The wave coming backwards, right? So all these seismic waves are also having the same properties. So these properties helps people to examine this Earth's interior in detail, right? So they can find out the velocities by measuring the time scales of these reflection and refraction phenomena, considering, okay, velocities and all. So people have understood the when the seismic wave penetrates from one place, I mean, from the crust to the interior, there is a sudden change of velocity that is referred as the Moho boundary, right? Crust mantle boundary. You learned this about this previously. So when the seismic wave penetrates from crust to the mantle, suddenly the velocity changes. Okay, the P wave velocity changes because you are encountering a peridotite type of a rock rather than felsic or intermediate rock, which is available in the crust as aluminium rich rock. So this rock difference causes the seismic wave to change their velocity. So it's more denser. The mantle is more denser, so the wave is bended. And also next is the boundary in the upper mantle. There is one place called, one zone called low velocity zone. So P waves, both S and P waves are transmitted, but there are some drops of velocities, which suggests that the material is not that rigid, because you know asthenosphere is not very rigid compared to the lithosphere, right? So asthenosphere is behaving like a gel, as if you can remember, it's like a jelly or gel. It's semi-solid, right? So therefore, there are drops of velocities in that regions as well. So people have figured out that physically this part of Earth should be not exactly rigid. So this is how people have come across different areas and different properties of the Earth's interior. Okay, and then from there onwards, 400 more deeper, 400 and 670. These are critical depths, characteristic depths. Exactly at 670, there are discontinuous 400 kilometers and 670 kilometers. So their P wave velocities increases very sharply, right? Sometimes it's like more than twice the velocity. Actually, this has been inferred as some chemical changes of material. That means some phase changes. Phase changes means the mineral changes. Phase means minerals. Mineral changes. For example, olivine. You know, in the mantle you have the olivine, peridotite, dominant mineral. That is available until this 400 kilometer depth. But from there onwards, olivine changes its form, but not chemically actually. It's physical change. It's a structural change. We call it ferroscite, right? So there is such change. So it's a kind of a polymorphic change, right? So high pressure variety change. It's like something like carbon changes into graphite or changes into diamond, like, right? No chemical change, but structural change is there. So such differences are there at 400 and 670. 670 is actually some more changes are happening. Garnet also changes, and quartz also changes. So these type of phase changes are there, so that people have understood there are some layers or some boundaries physically existing in the Earth's interior. So in this seismic refraction and seismic reflection helps us to understand about these layers. If this layer is denser, that means the velocity should be increased, faster velocity. If this layer is less dense, then the velocity should change low. So these changes are happening, and experimentally people measure, because seismograms or seismometers can be installed in on the Earth surface at different places, and some wave generators, some shock generators are also installed at these places, and one wave is generated, and at a different place that wave can be measured. For example, if there is an earthquake at the Indonesia, we can measure it at the United States, right? Because that seismic waves are coming or reaching the everywhere in the other place of the surface as well, right, after some time. That is the time interval it has taken to travel, right. Based on that, we can calculate the depth even, at what depth this earthquake happened. So likewise, all these measurements can be taken, considered. So this type of experiments have been conducting from long time ago. For example, the core-mantle boundary first discovered by Gutenberg, right? It's a German scientist. So it is called also as the Gutenberg discontinuity. Okay, so these are some experiments which have taken uh, up by different people. And another important thing is some of these P waves, if they reach the Earth's interior, uh, the latitudes or some angle, 105 degrees from uh, angle. I think you might not understand this clearly, so I will have to use a figure. I don't have that figure at this right now, but there is some angular angular distance where you see disappearance of these P waves. If these P waves are taking 105 to 140 degrees angle, they will disappear. That means we call it a shadow zone, right? So this thing, I think I have to explain with you. I explain you with the help of a diagram, right? So I will come to that in the next lecture, not today. uh, so which I skip for the time being. Okay, so we will move to this seismic wave reflection part. There, reflection means the bouncing off, the coming back, coming back. It's like the acting like a mirror, right? So this seismic reflection experiments have found that most of these seismic waves can be reflected backwards as well. So uh, once you have this reflection means there is no homogeneity in the interior, right? If it is very homogeneous, that means the traveled wave should continue traveling without disturbance. Reflection means it's a disturbance, okay? But it is coming back means it's a reflection. So this reflection actually happen as this outer core and inner core boundary is there. So whenever the seismic wave reaches the outer core and inner core boundary at the deep interior, these seismic waves comes back, reflect back. So it's really because, you know, the core, inner core is solid, right? Outer core is liquid, inner core is full of iron, solid iron. So that is the reason. Okay, it is reflecting. So it increases the velocity as well, because the density changes because of iron, the presence of ions. And later on it comes back, it returns back. Okay, so this is the reason for the solid inner core is the reason for this reflection. So this is how people have structured the earth into different layers, right? So different layers means from one layer to another. So these are very very important points, because people have used these seismic waves to understand the earth's structure, right? Earth structure. So with the aid of a diagram, I will explain about the shadow zones at the next time, because I don't have sufficient time. My connection is also not good, as I mentioned before. It's dying out, so therefore I may not have. But anyway, I will share this lecture note with you, because you have to read this. Definitely, you have to read this to get the complete understanding uh, as to how these P and S waves are helped in understanding the Earth structure. Okay, so all these densities and all of these layers, densities and velocities are measured experimentally as well. So we can measure the density. So for this P and S waves, normal average velocities are like 6 kilometers per second, right? Per second, 6 kilometers, right? P wave. S wave velocity is little below that like 4 kilometers per second line, right? So that means you can understand how fast these are traveling. So once you have an earthquake in one part of the earth, the other part of the world, people can detect it in few minutes later, right? So it can travel thousands of kilometers very quickly. Okay, so these are very useful for understanding uh, all these phenomena behind the all these physical properties and all related with the Earth's structure. Okay, so we call them anomalies. Actually, there is another term called anomalies because those are sudden changes. So these sudden changes are called anomalies. So usually these anomalies are produced as a result of density contrasts, density differences. So density differences can be caused by mineralogical changes. So you should understand the mineralogy controls all these physical parameters. So mineralogy means the composing minerals. What are the minerals available? For example, whether it is available with high iron magnesium rich minerals or just silica aluminum rich minerals, right? Low density and high density minerals. So this controls the heterogeneity of the Earth's layers, and that's why we have different differentiated planet actually based on these mineral changes. Okay, so